Welcome to the session on solution of system of equations. Simultaneous linear equations occur quite often in engineering and science. The analysis of electronic circuits consisting of invariant elements, analysis of a network under sinusoidal steady state conditions, determination of the output of a chemical plant, finding the cost of chemical reactions are some of the problems which depend on the solution of simultaneous linear algebraic equations. The solution of such equation can be obtained by direct method or iterative method. Here first we shall discuss direct methods. The first method is Gauss elimination method. Consider the system of simultaneous equations a11x1 plus a12x2 plus etc. plus a1nxn is equal to b1, a21x1 plus a22x2 plus etc. plus a2nxn is equal to b2, etc. an1x1 plus an2x2 plus etc. plus annxn is equal to bn. That is a system of n equations in n unknowns. This system can be expressed in matrix form as Ax equal to b, where A equal to the coefficient matrix A11, A12, etc., A1n, A21, A22, etc., A2n, etc., An1, An2, etc., Ann, which is an n by n square matrix. X is the column matrix of unknowns, that is column matrix of x1, x2, etc., xn, and B is the column matrix of constants b1, b2, etc., bn. To solve the given set of equations means to find the values of x1, x2, etc., xn such that they satisfy the given equations. In the Gauss elimination method, the unknowns are eliminated successively and the system is reduced to an upper triangular system from which the unknowns are found by the back substitution. The method is quite general and is well adapted in the computer operations. Here we shall consider the system of three equations in three unknowns for the sake of clarity. Consider the system a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z equal to d2, and a3x plus b3y plus c3z is equal to d3. A system of three equations in three unknowns. This is equation 1, this is 2, and this is 3. First we eliminate the unknown x from these two, that is from second and third equations. We use the operation equation 2 minus a2 by a1 times equation 1. And to eliminate x from this third equation, we use the operation equation 3 minus a3 by a1 times equation 1. Note that here a1 not equal to 0, we assume a1 not equal to 0. Then we will get the new system as a1x plus b1y plus C1 Z equal to D1. This term will be eliminated. The second equation will become B2 dash y plus C2 dash Z is equal to D2 dash, and the third equation becomes B3 dash y plus C3 dash Z is equal to D3 dash. This is a new system in 3 unknowns containing 3 equations. Now, we shall eliminate the second variable y from the third equation, from the last equation. This is equation number 4, this is 5 and this is 6. We eliminate the unknown y from this last equation. To this, we use the operation equation 6 minus B2 dash by B3 dash times equation 5. Then we will get the new system as A1x plus B1y plus C1z is equal to D1, B2 dash y plus C2 dash z equal to D2 dash, and C3 dash z is equal to D3 dash. This is equation number 7, this is 8 and this is 9. From this new system, we can find out the unknowns by the back substitution. That is, we will get z as z is equal to D3 dash divided by C3 dash, and we substitute this value of z in this 8th equation, we will get the unknown y, and we substitute the values of z and y in this first equation, that is in the 7th equation, we will get the unknown x. This is the method, Gauss elimination method. Now, we have to work out a problem. Apply Gauss elimination method to solve the equations x plus 4y minus z is equal to minus 5, x plus 4y minus z is equal to minus 5, x plus y minus 6z is equal to minus 12, and 3x minus y minus z is equal to 4. A system in 3 unknowns containing 3 equations. First, we eliminate the first unknown x from these 2 equations. We use the operation second equation, this is equation number 1, this is equation number 2 and this is third. We use the operation second equation minus first equation, and third equation minus 3 times the first equation. We will get the system as x plus 4y minus z is equal to minus 5. Here x minus x is 0, y minus 4y is minus 3y, minus 6z minus of minus z is 7z. minus 5z is equal to minus 12 minus minus 5 is 5 minus 12, that is minus 7. 3x minus 3x is 0. Here minus y minus 3 times first equation means this term will become 12y. That means minus y minus 12y, that is minus 13y, plus here 2z is equal to 19. This is fourth equation, fifth equation and sixth equation. Now, we have to eliminate the second variable y from this last equation. We use the operation equation 6 minus 13 by 3 times equation number 5. We will get the system as x plus 4y minus z is equal to minus 5, minus 3y minus 5z is equal to minus 7, and this term will become 71 by 3z. This equation will become 71 by 3z is equal to 148 divided by 3. This is the new system. From this system, we can find out the unknowns by using the back substitution. This is equation number 7, this is 8th and 9th one. By back substitution, we will get, from this last equation, we will get z equal to 148 divided by 71. The value of z is 148 divided by 71. From the 8th equation, minus 3y is equal to minus 7 plus 5z, which implies minus 3y is equal to minus 7 plus 5 into 148 divided by 71. Value of z is 148 divided by 71. We substitute this value in the 8th equation. On simplification, we will get y as, this implies y is equal to minus 81 divided by 71. Now, the 7th equation gives, from the 7th equation, we can write x is equal to minus 5 minus 4y plus z, which is equal to minus 5 minus 4 into minus 81 by 71 plus value of z is 148 divided by 71. On simplification, we will get the value of x as 117 divided by 71. Therefore, the solution of the given system is xyz is equal to 117 by 71, value of y is minus 81 by 71, and z is 148 divided by 71. This is the solution. of the given system. Now, we can perform the operation of elimination of unknowns by using the matrix method. That is, we consider the augmented matrix of the given system, and we can use the row operations to eliminate the unknowns. The given system is x plus 4y minus z equal to minus 5, x plus y minus 6z is equal to minus 12, 3x minus y minus z is equal to 4. The augmented matrix of the system is matrix AB is equal to 1 4 minus 1 minus 5, 1 1 minus 6 minus 12, 3 minus 1 minus 1 4. That is, we augmented the column matrix with the coefficient matrix of the system. Now, we have to make these two entries 0. We use the operation, R2 changes to R2 minus R1, R3 changes to R3 minus 3 times R1. We will get the matrix as 1 4 minus 1 minus 5. This will become 0. 1 minus 4 is minus 3, minus 6 minus of minus 1, that is 1 minus 6, that is minus 5, and minus 5 minus 12 minus minus 5 is minus 7. This is 0. Here 12, if we multiply with 3, this will become 12, and minus 1 minus 12, that is minus 13, 2 and 19. Now, we will make this entry as 1. That is, we use the operation R2 changes to minus 1 by 3 times R2. The system will become, this matrix will become 1 4 minus 1 minus 5, 0 1 5 by 3 and 7 by 3, 0 minus 13, 2 19. Now, we will make this entry into 0. We use the operation R3 changes to R3 plus 13 R2. This matrix will become 1 4 minus 1 minus 5, 0 1 5 by 3 7 by 3, 0 0 71 by 3 and 148 by 3. From this system, from this matrix, we can express the system as 1 into x plus 4 into y minus 1 into z is equal to minus 5. 1 into y plus 5 by 3 into z is equal to 7 by 3, and 71 by 3 z is equal to 148 divided by 3. By using the back substitution, we will get the values of unknowns. That is z equal to 148 by 71, y is equal to minus 81 by 71 and z equal to 117 by 71. This is the Gauss elimination method. Now we shall discuss another method known as Gauss-Jordan method. The Gauss-Jordan method is a modification of the Gauss elimination method. In this method, elimination of unknowns is performed not in the equations below, but in the equations above also. Ultimately, reducing the system in a diagonal matrix form, that is, each equation involving only one unknown. We have to work out a problem using Gauss-Jordan method, that is, solve x plus y plus z is equal to 9, 2x minus 3y plus 4z is equal to 13 and 3x plus 4y plus 5z is equal to 40. We consider the augmented matrix as matrix AB is equal to 1 1 1 9, 2 minus 3 4 13, 3 4 5 40. This is the augmented matrix corresponding to this system. We have to make these two entries 0. We use the operation R2 changes to R2 minus 2R1 and R3 changes to R3 minus 3R1. This matrix will become 1 1 1 9. This is 0 here, minus 5 2 minus 5, and the third row will become 0 1 2 and 13. Now we will make this entry into 1. We use the operation R2 changes to minus 1 by 5 times R2. This matrix will become 1 1 1 9, 0 1, minus 2 by 5 and 1. Third row is 0 1 2 and 13. We make these two entries into 0. We use the operations R1 changes to R1 minus R2. Using the second row, we have to make the first row, entry in the first row will become 0 and this entry into 0. R3 changes to R3 minus R2. The matrix will become 1 0 0. This is 1 here, other 0. Here minus 1 minus minus 2 by 5, 7 by 5, 8. Here minus 2 by 5, this is 1, and the third row will become 0 0, 12 by 5 and 12. This is the new matrix. And now we use the operation R1 changes to R1 minus 7 by 5 times R3. we have to make these two entries into 0. We use the operations R 1 changes to R 1 minus 7 by 5 times R 3 and R 2 changes to R 2 plus 2 by 5 times R 3, R 2 plus 2 by 5 times R 3. This matrix become 1 0 0, this is 1, 0 1 0 3 and 0 0 1 5. If we use these two operations, the matrix will become like this. Using this augmented matrix, we can express the system as x is equal to 1, here y is equal to 3 and z is equal to 5. That is, in the Gauss-Jordan method, we will make the entry, we have eliminated the unknowns from the rows below and above from each rows. This is solution of the given system is x is equal to 1, y equal to 3 and z is equal to 5. Thank you for watching this session. We will meet again in another session. Thank you.